Good afternoon, all of you. Should we start?
Afternoon, Dr. Asha.
Okay, I think we can start now. Okay, we'll start now. I hope screen is visible. Okay, so in the previous lecture, we have seen the discrete time Fourier transform, how it is used. Is in discrete time Fourier transform, basically we convert the time domain discrete values into the frequency domain continuous values. Okay, but in case of discrete Fourier transform, earlier it was DTFT, that is discrete time Fourier transform. This is basically today's lecture is focused on the discrete Fourier transform, that is DFT. Okay, so in case of DFT, this DFT basically deals with the conversion from discrete values, conversion of discrete time domain values to the discrete Fourier, discrete frequency domain values. Now, in case of DFT, we will convert the discrete time domain values into the discrete, not continuous, in the discrete frequency domain values. Okay, so basically we are having, so we can say that the DFT basically converts time domain discrete values into frequency domain discrete values. Here n is the integer, k is also the integer. K is used for the frequency domain. Okay, now what was the problem with respect to DTFT basically? Now in case of the DTFT, we produce the continuous frequency values in the frequency domain. It was continuous values. The x-axis, that was omega, in case of DTFT was the continuous one. Okay, now in that case, if there are many, in case of continuous values, we will be having many inputs to the frequency omega. Now, to compute a Fourier transform in the digital system for this continuous frequency, it was maybe impossible. We cannot say mostly impossible, but it will require very high powerful hardware or high storage values. Now, for to overcome this problem, so the entire we cannot apply the Fourier transform to the continuous one. So if we discretize that frequency domain, continuous frequency domain values, then it will be easy to apply the algorithms to compute the transform on that. Okay, so therefore to overcome this problem, the discrete Fourier transform is introduced. Okay, so in that case, basically both the time domain and frequency domain values are in discrete form. Okay, so we are having many advantages of discrete form. So this is one of the advantage. Okay. Now we know that x of n, we are having x of n signal. So this x of n is having values from n equal to 0 to n minus 1. Correct. Now, in case of DTFT, what we got is this x of n we converted into a capital X e to the power j omega. Right. Now, this is basically, if I expand this, so I can say this is x of 1 e to the power j0. If I expand omega, so this I will say in discrete form x of 0, this is x of 1 e to the power j omega plus x of 2 e to the power j uh, 2 omega till what? Till, if I discretize this, so I can write in like this. So this is up to x to x, this should be capital N minus 1 e to the power j capital N minus 1 omega. Okay, so this is capital N. So if I say this x of n is a sequence and this is having size n is basically the size of this sequence. Okay, so this we can represent from 0 till we are having values from 0 to capital N minus 1 for this sequence x of n. I'm saying this x of n discrete sequence having values from 0 to capital N minus 1 because n is the size of the sequence. Now with the DTFT we have converted this x of n to a capital X e to the power j omega. These are the sign conventions. Now again if I want to discretize this into this many intervals, this how can I can expand this in like this. Okay, so x of 0 e to the power this like till n minus 1 values. Okay, okay, so this is basically what, this is basically the sample values at endpoints. These are the sample values, samples of x, I can say. These are the samples of x at endpoints. Okay, now when we write this in a discretized frequency domain, so we can put subscript k here. Okay, so I can write this x e to the power j omega k here. Okay, and this k is basically will vary from 0 to n minus 1. Okay, instead of this each value I can say this is k times omega. Okay, and k here is the integer, so that you have to remember here. Okay, now we said that, so we have a region for omega from 0 to 2 pi. Okay, so if I plot this, so how I can plot this omega like this. Okay, now suppose I say that I am having omega here which start at omega equal to 0. This is pi by 2, this is pi, this is 3 pi by 2 like this. Okay, and we represent with the circle like this. Okay, and this is suppose moving with the moving in anti-clockwise direction. Omega is moving with anti-clockwise direction. Now suppose I say that I'm having sequence x of n and this is equal to from 0 to n minus 1, which is having n number of samples. So I can make n number of parts of this circle. Okay, so I will say that x of 1 will be here, x of 2 will be here like this. So I have to make n number of parts of this circle. Okay, so I will say that how to discretize. This is the sampling or discretization process, we can say that. Okay, so this last value I will say this is x of n minus 1. Okay, now can we find this interval, how much this angle will be? So this total angle is what this is, this region is of 2 pi, correct? And we are making n number of samples of from this 2 pi region. So this, the single value I can say, this single value is nothing but 2 pi total region divided by n number of samples. Okay, so at every this sample, at every this interval 2 pi by n interval, we will get the values of this. Okay, like suppose if any some particular sequence is having 4 samples. Now in that case, how we'll calculate the discretized values here? So in that case, we will take first n equal to, so this will goes from 0 to 3. So if I put 0 value here, first interval is at 0, then second interval this is 2 pi by 4. Okay, n is having 4 values. Okay, so 2 pi by 4 is means pi by 2. Then third value is 2 pi by 2. Fourth value is 3 pi by 2, like this. So this is basically what will this k, we are multiplying with the integer. Okay, so this k will vary from 0 to 3. So therefore, here we have multiplied with this k, and this k is basically is the integer. Okay, got this idea how to discretize this? Okay, now the representation, if I say, basically this converts a DFT, basically converts x of n to capital X of k. Okay, in case of DTFT it was x of omega, you remember, no? This is DFT. DTFT, what we got here, DTFT we got x of n, from x of n, x of omega, and this omega was continuous in this case, and this is discrete in this case. Okay, now how to define this DFT here? So this DFT, basically I can write this. So I say that this x of k is DFT of what? DFT of x of n. Okay, and this I can say that this is basically summation from n equal to 0 to n minus 1 x of n e to the power minus j, here now 2 pi by n k into n. Okay, this is similar to the Fourier transform, but this is only for the finite sequence. This is only for the finite sequence. Please remember this. Okay, therefore the summation goes from 0 to capital N minus 1. Capital N represent the size of the sequence. Small n is basically the integer. Again, k is the integer. Okay. Now here, instead of omega, what we have written here? Now this is the discretized omega. 2 pi by capital N into k. This is basically the discretized omega. Okay. Again, this k will go from 0 to n minus 1, and this n is also goes from 0 to n minus 1. Okay, so basically what we are converting x of n into the x of k. This is capital. capital X of k. This is small x of n. Okay. So this is the sampling. Now this frequency domain sampling. This is in the graphical, the x and y axis format you can see here. Now in the uh, frequency domain representation, basically we are having on the x-axis omega, on the y-axis it may be anything, like this is magnitude of x of omega, you may be having the angle or the magnitude in dB or power or energy, like this you will be having on the y-axis. Now suppose if I want to make the sampling of this continuous frequency values, so the sampling we are taking at the each delta omega interval. Okay, so this delta omega, basically I am saying that this delta omega is nothing but 2 pi by capital N. This is nothing but what? 2 pi by capital N. Okay. Now in time domain, we know that how to do the sampling. So basically we take the sampling time. So that suppose I say this is TS is my sampling time. So we multiply this with the n number of integers and we'll take the samples at each interval. Okay. So we say that this is n times TS. Okay. And at each interval, we will take the sample values. Okay. Now in the frequency domain also we are having the similar process. Okay. So one sample we are taking at each delta omega interval. Okay. So and this delta omega is nothing but 2 pi by capital N. Okay. This is delta omega is equally spaced frequency within this range 0 to 2 pi. So we are having region from 0 to 2 pi frequency range. Beyond 2 pi, basically, this is the repeating sequence. That is, we are saying it is periodic. Therefore, we will get the repetitive values. Okay. So we will be having n number of samples for this particular frequency values. Now, if in time domain T is n times Ts is used to sample the time, in frequency domain, we say that this now for time domain, this is T. For frequency domain, we are having omega here. Now this omega, we can say this is basically K times delta omega. Okay. So this is K times delta omega. And both k and omega k and n are the integer numbers in this frequency domain. Okay. Now in time domain we said that this fs, that is sampling frequency, fs is what? This is the sampling frequency. This sampling frequency must be greater than equal to 2 times the natural frequency, whatever the original frequency signal is there. So it should be greater than equal to 2 times this. This is to avoid the aliasing in the system. Okay. Now in case of frequency domain, this aliasing can be avoided when n is chosen as it should be greater than equal to the length of the signal in the time domain. So this is the, so we need to choose proper n values. That means the size of this particular sequence or signal should be chosen properly so that we can eliminate the aliasing problem in the signal. Okay. Now, in computing the discrete Fourier transform, the frequency range will always start at omega equal to 0 and this will end at what? Omega equal to 2 pi minus delta omega. This you need to Understand? Okay. This should be end at 2 pi minus delta omega is again 2 pi by n. Okay. So in the previous case, what we have, I have said you, if I am having 4 number of samples, if I say I'm having n equal to 4, so it should end at what? 2 pi minus 2 pi by 4. So that is what? This is pi by 2. So the last sampled value is at 3 pi by 2, like this. Okay. So you have to always start with omega equal to 0 here. Okay, and this is uh, the formula to get the DFT of x of n. Okay, like this is, we said this is the forward discrete Fourier transform. So we are also having the inverse discrete Fourier transform. That is called as IDFT. Okay, this is basically the inverse discrete Fourier transform. Okay, now in case of inverse discrete Fourier transform, what we are getting? We can get back signal x of n from what? X of capital X of k. Okay, like in our previous lecture, we have seen discrete time Fourier transform, where we convert x of k, x of n to x of omega, and we can get back this x of n sequence from x of omega with the inverse discrete time Fourier transform. Similarly, this is says, we says that this is the inverse IDF, inverse DFT. Okay, and here you can see, here we are having summation in both the cases. Okay, like in case of inverse discrete time Fourier transform, we were having the integral. Why integral was there? Because that there x of omega was there, and that omega was continuous in time. That was continuous values. Now here we are having the discrete values, therefore we need to take summation. Okay, again that need to average, that is 1 by n, you need to multiply here. So in the previous case, we was having the 2 pi here, 1 by 2 pi integral from minus pi to pi, like this was there. Okay, so you just uh, remember this DFT conversion formula. Okay, so I can get x of k from x of n when I will do summation from n equal to, basically you can say here, this should be finite. So from 0 to n minus 1, this is from 0 to n minus 1 x of n e to the power minus j 2 pi by n k into n. Okay, this is the forward transformation. And if I want x of n back, so 1 by n, again summation from k equal to 0 to n minus 1. Now this is x of capital K, capital X of small k e to the power, here not minus sign is not there, this is plus j 2 pi by n k into n. Okay, this is the note here. One, this is the example here. Now we'll take, before this we'll take one simple example. Okay, suppose I'm having the sequence x of n. Suppose this x of n is delta of n. Delta of n is what? Impulse signal. Okay, so this impulse signal is basically having value 1 at n equal to 0 only. Okay, now for this type of signal, what is the if you apply DFT on this type of signal, what you will get? X of k is what? Summation from n equal to 0 to n minus 1 x of n e to the power minus j 2 pi n k into small n. Okay, now for delta of n, we know that we are having value 1 for n equal to 0. If in n equal not equal to 0, then it is 0. So only we will keep n equal to 0 here, otherwise values are zeros. Therefore, for x of 0, we are having 1. Therefore, I say this is 1 e to the power j0, that is 0 is 1. Therefore, the answer is what? The x of k of the impulse response is basically equal to 1 for all k varies from 0 to n minus 1. Okay, 0 to n minus 1. Okay, so for all k's from 0 to n minus 1, it is equal to 1 only. Okay, now suppose if I delay this with m samples, so I say delta n minus m, delay of m samples, and this m can be from 0 to n minus 1. Okay, now this is the sequence. Now in that case, now here delta of n minus m is what? For n equal to m, you will be having value of 1. If n is not equal to m, then it is 0. Correct. So you are having only value at n equal to m. Now, if I apply DFT for this sequence, so capital X of k, I can say capital X of k is equal to summation from n equal to 0 to n minus 1 delta n minus m e to the power minus j 2 pi by n. This is small k into small n. Okay. Now, in this case, I can say that for n equal to m only I am having value 1. Otherwise, I am having value 0. Okay. So, I will say that the output of this is basically we are having value 1 at n equal to m. So we left with what? We left with e to the power minus j 2 pi by n into k into n. Now here k will vary from 0 to n minus 1. Okay, so if I put k equal to 0 here, so the first value e to the power 0, that is 1, you will get. Second value, what you will get? If you put here 1 here, so minus j 2 pi m upon capital N. Are you getting this? Because we are having here, you need to write n equal to m, because we are having only one value at n equal to n. Okay, so instead of n, you will be having m here. At k equal to 2, e to the power minus j 2 pi into 2m divided by capital N. So like this, you will get the values till what? Till n minus 1, right? that is e to the power minus j 2 pi into n minus 1 divided by n into small m. So like this sequence you will get here. So can you differentiate these two examples? Have you understood this? Yes, students. Are you getting the point here?
Yeah, doctor.
Okay, it is okay with you, no? So like this, you can also try the uh, another example. Okay, before that, we'll take this example only. Okay. Now, suppose I say I'm having this sequence h of n. Okay, now I need to find the, if I apply DFT, so find DFT response of this h of n. So I will get capital H of small k. Okay, so find h of k. This is the example. Okay. Now from this signal or sequence, you can say that I'm having the size n equal to 4 here, capital N equal to 4. Okay. So this is the length of this signal. Okay. Now the DFT is basically computed from what? Computed from 0 to n minus 1. Therefore, in this case, it is from 0 to 3. Okay. So this is k, I will say from 0 to 3. Okay. Now, first step is what? Apply DFT formula here. So I will say that capital H of k is equal to summation from n equal to 0 to n minus 1 h of n. Here h is used, e to the power minus j 2 pi by capital N small k into small n. Okay. Now if you put value n equal to 4 here, so you will get this. Okay. So in this case, what you will get here? H of n e to the power, if you simplify this is j times pi kn divided by 2. Okay. Now find value for each n. So I will say this is h of h each k. This is k. Because k we are varying from 0 to n minus 1. Okay. So here k equal to 0. So if I put k equal to 0, so this is h of n e to the power 0. Okay. And again, we need to do the summation over here. Okay. So if you vary n from 0 to 3, so if you add up all this thing, this is anyway, this is 1. Okay. Now what is remaining here? Summation of h of n from 0 to 3. So summation of this h of n means the addition of all this given sequence. Okay. So if we add this, so this what you will get? 1 plus 1 plus 1 plus 1, you will get 4 here. Okay. So I will say that h of 0 equal to 4. Now similarly, I can calculate h of 1, h of 2, h of 3. Okay, till 3 we can calculate here. Okay. So can you calculate h of 1 here? What is the value for h of 1? What you will get? So if I put k equal to 1 here, so this is what? E to the power j pi n by 2. and this is h of n. Okay, now first is put n equal to 0, so this term will be 0, so h of 1 is 1, therefore this is 1, plus if you put n equal to 2 here, no, n equal to 1 here, so h of 1 is anyway 1 e to the power minus j 2 pi 1 by 2, so this is this. If you put 2 here, so you will get this. If you put 3 here, so you will get this. Okay, now what is e to the power minus j pi by 2? This is what, how you expand this. This is cos minus j sine of pi by 2, correct? So if you do the trigonometric expansion of this, so this is cos of pi by 2 minus j times sine of pi by 2. Cos pi by 2 is what? 0. Sine pi by 2 is 1. Therefore, minus j is here. Okay. Similarly, you can calculate for this and this. For this, you will get value minus 1 here. For this, you will get plus j. Okay. So, if you add up all this, you will get output 0 here. Okay. So, I will say capital H of 1 is nothing but 0. So if you put k equal to 2 here, again, this is what? J into 2 pi by 4, that is pi by 2 into n. Here 2 will cancel. K equal to 2 I am saying, therefore divide by 2 and this 2 will cancel. So you will left with this e to the power minus j pi n. Again, put values of n from 0 to 3. So you will get this, and if you add up all this, you will get 0 here again. Okay. Similarly, for h of 3, if you calculate, you will get 0 here. So the final answer here, this is h of k. This h of k is nothing but 4000. So I will get this as an output of this h of n signal. Okay. And if I want to represent this in graphical format, so on the x-axis, I will say this is k, and on the y-axis, or you can represent with the magnitude only. So this is h of k. So at n k equal to 0, you will be having 4. At k equal to 1, it is 0, 2, it is 0, 3, it equals 0. Okay, so in graphical way, you can represent like this. Okay, so here these 4 samples are enough to represent the frequency response in the range from 0 to 2 pi. Okay. So we have taken basically sample at each delta omega, and this delta omega is nothing but 2 pi by 4, which is equal to pi by 2 radians. So at each pi by 2 radians, we have taken this sample. Okay, so we can say that at 0, at pi by 2, at pi, at 3 pi by 2, we have taken the samples and calculated the capital H of K. Okay. Okay. So in this example, basically this capital N is equal to 4 is similar to the signal length. And this is the enough to represent the frequency response of the particular signal. Okay. Now, from this h of k, we can get back the signal h of n. Using inverse from h of k, I can get back signal h of n using inverse transformation, IDFT. Okay, so for that case, you need to apply this IDFT formula. Okay, so I can get h of n from h of k with this. So 1 by n summation of k over 0 to n minus 1. Here e to the power plus j 2 pi k n by n. Okay, so h of k, what we have just now calculated, this h of k is 4000. This h of k is 4000. So we'll check whether we will get 11111 from this IDFT. You should get this value. Okay. Now if I apply this formula and find out the value of h of n, so first value, I will say that this h of n is 1 by 4 summation k equal to 0 to 3. If I simplify this, what I will get here, this j pi by 2 kn. Okay, if I put n equal to 0 here, so if this is 0, this term will be 1. Okay, so this is what summation of h of k from this. So this is 4 plus 0 plus 0 plus 0. So you will get 4 there and divide by 4. So you will get value 1. Okay, this is what 1 by 4. This summation of this is what 4 plus 0 plus 0 plus 0. So 4 by 4 you will get 1. So like this, you can calculate for n equal to 1. So in case of n equal to 1, you will get this e to the power j wala term. Okay. So this term you will get, and if you do summation of this, then you should get output this one. Okay. You can do as a homework here. So you try to solve this example at home, because in exam you need to do all these steps. You cannot directly write here. Okay, you have to write in stepwise. So after doing the calculation, you will get here value 1 for h of 2. Also you will get 1. This h of 3 also you will get 1. So you will get the original h of n signal. Okay, so we got the original signal using inverse DTFT. Now, suppose I am having this h of n, which is equal to x of n. This is another example where h of n and x of n is given. This is equal to basically 1 and 1. The sample size is 2 here. Okay. What is asked here? To find y of n using frequency domain computation is asked here. Okay. Now, first, what we do, we will first find out the x of k and h of k. Okay. So, this is basically equal because this given sequence is equal. So, first find out h of k, x of k. Now, this is very small sample. Size is very small. That is capital N equal to 2. So, n will vary from 0 to 1 only. Okay. So, find h of 0, h of 1. So, you can say here if you do the calculation, put n equal to 0, so this term will vanish. If this is equal to 1, so you will left with summation of this h of n. So 1 plus 1 is 2 here. One plus 1, 2 here. Therefore, this is 2. For n equal to 1, you just calculate this. So you will get here 0. So what you got here? So x of k, which is equal to h of k, this is you got 2 and 0. Okay. What is asked? Y of k. Okay. So y of k is basically this is product of h of k into x of k. In frequency domain, this is the product. In time domain, it was convolution of x of n and h of n. But here, what is asked? Y of n using frequency domain is asked. Okay. So in frequency domain, we can multiply this. Okay. So if you multiply this, what you will get? 4 and 0. 2 0 2 0. If you multiply, this is 4 0 you will get. So y of k is basically equal to 4 0. But what is asked here? Asked y of n. So again, you need to convert back y of k into y of n. So for that, you need to use IDFT here. Okay. So if we use IDFT, so y of 0 will get 2 here, y of 1 will get 2 here. Okay. So what is the final answer here? 2, 2. Okay. This is 2, 2 here. So using frequency domain, what we are getting here? 2, 2. But if we do the convolution, if we calculate the y of n using time domain, so in that case, what you will get here? You will get this output. So the result with the frequency domain computation, we are getting the wrong result. This result is not similar with the time domain convolution. Okay. If you convolve x of n and h of n, so you will get the output y of n equal to 1 to 1. Okay. So why there is this incorrect answer using the frequency domain computation? This is because we are having sample size very less. So here the sample size was 2 only. Okay. So because of insufficient sample size, we are getting the wrong result. Okay. So the output y of n is having length equal to 3. Okay. So at least we should consider the sample size equal to 3 to get the correct answer. Okay. So this thing you need to understand here. The choice of sample size is very important. Okay, this is equal to 3. You need to consider at least 3. Okay. Now, the same example, if you choose sample size 3, and if you do the calculation here with n equal to 3, so you can see h of 0 you will get 2, h of 1 you will get value e to the power j60, h of 2 you will get e to the power j60, this is minus plus. Okay. So h of k you are getting this. If you want to calculate y of k, so this is h of k into x of k, and this is equal to what? This is equal to this. Okay. Now if you do the inverse transformation to get back value y of n, and if you find out y of n here, so you will get 1, 2 and 1. Okay. So the final answer is 1 to 1, which is correct one. So here, when we have chosen n equal to 3, we are getting the correct answer. And if the sample size n is less than 3, we are getting the wrong answer. Okay, so we are getting the same result even in the frequency domain computation. Okay. Now, this is another example where the size of x of n and h of n is different. So this is having size 2, this is having size 3. Okay. And what is asked here? To find y of k. Now, to find y of k, DFT for both x of n and h of n must be computed where both DFT having same n. Okay, because we are multiplying this x of n and h of n, or x of k and h of k. So this should have the same n. Okay, then only we can multiply each value, that is at each omega we can multiply this. Okay, now if we choose different n values, now what will happen? If you choose n equal to 2 for x of n, then delta omega we are getting pi here. Delta omega is what? 2 pi by n, that is 2 here. So this is pi. So k will vary from 0 to 1, and this is referred to omega 0 to pi. Now for h of n, where n equal to 3, for this calculate delta omega here. So you will get delta omega is 2 pi by n, that is 2 pi by 3. So we are varying k from 0, 1, 2. Okay. Now this is referred to omega what? Omega 0, 2 pi by 3 and 4 pi by 3. So we are getting different omegas here. So how we can multiply this? Okay. So therefore for different n, it can be seen that even at similar k values, the omega value is different. For this k equal to 0, it is 0, but k equal to 1, it is omega. But in this case, for k equal to 1, it is 2 pi by 3. Okay, so we are having different omega values for similar k value. Therefore, the multiplication of this x of k and h of k will be wrong. Now, to get the correct answer, n must be at least with the minimum value, which is 4. Okay, so n must be set at least with its minimum value, which is 4, and both DFT of x of n and h of n must be computed based on the 4-point DFT. Okay, and if you do the computation for this, so you will get a result like this. X of k you will get like this, h of k you will get like this, and you can calculate y of k by multiplying this. So you will get this. Okay, and you can again convert back y of k into y of n, and you will get the original signal output like this. Okay. So this is some relationship of DFT and DTFT. Okay. Like in case of DTFT, we have seen some properties of DTFT. Now, these are the properties of discrete Fourier transform. Okay. So the notation property, this is the notation basically. This is time domain we represent with small x, small n, y, small. This is with the small. Okay. In the frequency domain, this is capital rater and this is k. y of k, x of k, h of k, like this. The first property is the periodicity. Okay, so this is basically periodic in nature, therefore I can say that DFT is also periodic. So this is x of k is basically equal to x of k plus n. Okay, at after every n sample you will get the repetitive value. Okay, therefore this I can say x of n equal to x of n plus n, same x of k equal to x of k plus n. Linearity, so this is basically linear in nature like DTFT. DFT is also a linear in nature, therefore alpha times x of n plus beta times y of n, b times y of n. So you will get a times x of k plus b times y of k. Okay, after DFT you will get this. So I will say this is linear in nature, this is periodic in nature. Okay, circular time shifting. So if there is a time shifting of nd, then in frequency domain you will get multiplied by this factor e to the power j 2 pi k nd by n. Okay, instead of n you will multiply by, here this is nd, whatever time shift is there you need to multiply by this. So this whole term is multiplied with the x of k. This is time shifting, circular time shifting. So in DFT basically we are having circular effect here. Okay, now circular frequency shifting, if you are having frequency shift in this, so here is the, if what, how much frequency shift is there, frequency shift of kd here. So in the frequency domain when you apply DFT, so this is basically k minus kd. Okay, so circular time shift is very important property, circular frequency shift is also very important property. Circular convolution, this is x of n, in this is circular convolution is basically inside this circle, this is n is here. So this is basically multiplication in the frequency domain. Okay, if there is a multiplication, then this is circular convolution in the frequency domain. Okay, vice versa. And this is Parseval's theorem. So summation from n equal to 0 to n minus 1, x of n, y conjugate of n is there, then this is basically the frequency domain output, that is 1 by n, summation k equal to 0 to n minus 1, x of k, y conjugate of k, like this. Okay. Okay, so this topic DFT, discrete Fourier transform, please read some portion from the book which I have shared with you. Antonio's book, here's the chapter number. Chapter number 7. Okay, please read this chapter. So you can read the 7.1, 7.2 till 7.6, and some portion of 7.10 periodic convolutions you can read. What is time domain periodic convolution? What is a frequency domain periodic convolution? Okay. There is 7.11, that is fast Fourier transform. So basically fast Fourier transform is not another type of transform. That is actually the discrete Fourier transform only. That is the DFT only. Okay. So therefore, one more section is there. We'll see this I think FFT is not there in your syllabus, but the initial portion of this chapter number 7 you can read. So you will get more insight into this topic, discrete Fourier transform. Okay. So for today, actually, I will stop here. So at home, you please try to solve these example, whatever we have covered in this lecture. Okay, try to solve this by hand. Then only you will get the idea. Okay, so do you have any doubt today?
So far, still okay, doctor.
Have you understood how to solve DFT, inverse DFT? Okay, so please read out this topic from the book, and if you are having any doubts, then you can ask me in the tutorial session. Okay.
Okay,
Okay,
doctor.
doctor.
Thank you.
Okay, so for today we will stop here. Thank you. You can also post it in our channel here in Moodle, Intel, and here also you can post it.